So far we have seen some constructional features of a three-phase transformer, and we have indicated that even for the simplest of the three-phase transformer there are 6 windings and 12 terminals. So, there are 3 high voltage windings and 3 low voltage windings. This is the minimum. In many cases, either the high voltage winding or low voltage winding can be split into 2 parts, giving 9 sets of windings. Even in the simplest case, there will be at least 6 windings. Now, each of these high voltage or low voltage winding can be either star connected or delta connected. And if one set is split into 2, it is also possible to have a zigzag connection. So, theoretically either set of winding, high voltage or low voltage, can be star, delta or zigzag connected. So, in order to completely specify the transformer winding connection, we have to mention the high voltage connection, whether it is star HV connection, whether it is star, delta or zigzag. Similarly, the LV connection, whether it is star, delta or zigzag. However, that is not sufficient. In our last lecture, we have seen how to find out the line voltage and current as well as phase voltage and current conversion ratios of a 3-phase transformer given the winding turns ratios. So, we have seen that the voltage magnitudes on either sides are different. That is the purpose of the transformer. However, a closer scrutiny will reveal that not only the magnitudes of the high voltage and low voltage sides are different, in many cases they are also not in phase. So, when we specify the winding connection on the high voltage and low voltage sides, in addition to specifying whether they are star, delta or zigzag connected, we will have to also specify what is the phase angle between the high voltage line to neutral phasor, line to neutral phasor of high voltage, the angle between line to neutral phasor of high voltage and low voltage winding. So, a complete specification of 3-phase transformer winding connection will involve specifying the high voltage side connection, star, delta or zigzag, low voltage side connection again star, delta or zigzag, and the phase angle of the low voltage line to neutral voltage phasor with respect to the high voltage line to neutral voltage phasor. For example, we may specify the connection to be Y D plus 30 degree. This means the high voltage is star connected, the high voltage line to neutral phasor, high voltage is star connected, the low voltage is delta connected, and the line to neutral phasor of low voltage winding leads the, this is high voltage line to neutral phasor, this is low voltage line to neutral phasor. This leads the high voltage line to neutral phasor by 30 degree. So, this kind of specification is called the phase group specification of a 3-phase transformer. The phase group specification involves 3 specifications. One is the connection of the high voltage winding, connection of the low voltage winding and the phase angle between line to neutral voltages of low voltage winding with respect to the high voltage winding. Now, this phase angle, there are two conventions of specifying the phase angle. Before we talk about the convention, let us assume what kind of phase angles are possible. There are four types of phase angle that are normally possible. The phase angles can be either 0 degree, that is the line to neutral voltage phasor of both sides may be co-phasor, or 180 degree, that is they may be opposite in phase. The one can, the low voltage winding voltage phasor may lag the high voltage winding by 30 degree, or it may lead by 30 degree. So, correspondingly there are four groups. This is called group number 1, this is group number 2, this is group number 3, this is group number 4. In many cases, particularly in older installation, this phase angle is indicated by a clock number. For example, if we take the analogy of a clock and say that the minute hand represents the line to neutral phasor of the high voltage side and the hour hand, which is smaller, represent the line to neutral phasor of the low voltage side, then 0 degree phase angle, this is high voltage line to neutral phasor and this is the low voltage neutral phasor. On a clock, if we assume this to be a clock, then this is 0 hour. So, this is called 0, clock number 0. Similarly, for 180 degree, this is the high voltage phasor, this is the low voltage phasor, their angle being 180 degree. So, on a clock, this represents 6 o'clock. So, this is clock number is 6 for this. For minus 30 degree, this is the hour hand, this is the minute hand representing the high voltage side line to neutral phasor, and this is the low voltage side neutral phasor, line to neutral phasor. This is HV, this is LV. Here the line to neutral phasor of the LV side leads the line to neutral phasor of the HV side by 30 degree. So, this is group number 4, this is called this represents 11 o'clock, therefore, this clock number for plus 30 degree is 11. Similarly, for minus 30 degree, this is HV line to neutral phasor, this is LV line to neutral phasor, this represents 1 o'clock, therefore, this clock number is 1. Hence, actually the phase groups can be specified either in terms of phase angle or in terms of clock number. Therefore, for example, this y 0 degree can also be written as y 0. This is the phase angle. This is clock number. Similarly, D 180 degree can also be written as D 6. This is the clock number representing 180 degree phase shift. Let us say Y D plus 30 degree. This will be corresponding clock number representation will be YD 11. Let us say Y Z minus 30 degree. This will be corresponding clock number representation will be Y Z 1. So, this is the correspondence between phase angle representation and clock number representation. They are interchangeable, and in many cases the phase groups will be specified like this, in many cases it will be specified like this, but they represent the same thing. Let us see what are the different combinations possible. For example, it is easy to understand that we can always have a Y 0 D 0 or D Z 0. In all cases, of course, the high voltage and low voltage side connections may be interchanged. This is one of the possible phase groups, set of phase groups with 0 degree phase angle. We can also have Y 6 D 6 or D Z 6. However, it is interesting to note that YZ 6 or 0 is not possible. Why? We will see shortly. These are 0 degree and 180 degree phase shifted phase groups. For plus minus 30 degrees, you have D Y 1, this is minus 30 degree, then or you can have Y D 1 or you can have Y Z 1. Again, the high voltage and low voltage side connections can be interchanged. However, DZ1 is not possible. So, this was 0 degree phase shift, this is 180 degree phase shift, this is minus 30 degree phase shift, and then you can have D Y 11 Y D 11 and Y Z 11. These are plus 30 degree phase shifted configuration. The configuration that are not possible are Y plus or minus 30 degree, this is not possible. D plus minus 30 degree, this is also not possible. Y Z 0 degree, not possible. Y Z 180 degree, not possible. D Z plus minus 30 degree, this is also not possible, or Z D plus minus 30 degree, this is also not possible. So, we have seen that there will be 12 different connections of 3-phase transformer. Let us see how these connections are made. Let us start with the simplest one, that is Y 0 degree. So, how the Y 0 degree line to neutral phase voltages will look like, the phasor diagram. Let us say this is phase A of the high voltage side, and this is phase B of the high voltage side, this is phase C of the high voltage side. The phase group says that the line to neutral voltage of the low voltage side will be co-phasor to the line to neutral voltage of the high voltage side. Therefore, if this is the neutral, then on the low voltage side, this will be phase A, this will be phase B, this will be phase C, and this will be the neutral. Now, let us say this A is actually the voltage phasor A2 A1, and on the low voltage side this voltage phasor is between small a2 and small a1. This is between B2 and B1 and B2, and this phasor is between C1 and C2. This is again between B1 and B2. This is between C1 and C2. Now, from this voltage phasor, it is easy to see how the connections will look like. For example, if these are the windings, high voltage winding, this is A2, A1, B2, B1, C2, C1, and these are the low voltage windings, A2, A1, B2, B1 and C2, C1. Then from this phasor diagram we can see that the high voltage neutral is formed by joining capital A1, capital B1 and capital C1. So, this will be the neutral point N, this will be the line A, this will be line B, this will be line connected to line C. Similarly, on the low voltage side the neutral is formed by connecting terminals small a1, small b1 and small c1. and the lines are obtained from the other side. So, this is A, this is B, this is C. So, this is what the connection y 0 will look like. Next, so let us try to do the same thing with a 6 connection. Let us say DD6. What does DD6 means? That is the line to neutral phasor of high voltage side and low voltage side should be in phase opposition. So, let us again see so, this is the line to neutral phasor of the high voltage side A, B, C. Then the low voltage side we want it to be like this. This we want to be A, this B and this C. Again let us say, however, please understand that the connections on the windings are now delta. Therefore, the line to neutral voltage is not same as the voltage across a winding. However, we will still assume that the lines are connected to A2 this is terminal A2, this is terminal B2, this is terminal C2. Similarly, on the low voltage side, this is terminal small A2, this is terminal small B2 and this is terminal small c2. Then how do we make the connections? Please remember that the connections has to be such that the winding voltages are either in phase or they are in opposite phase. So, what will be the voltages across the windings? It will be the line voltages. So, where will be terminal A1, so let us say this is terminal A1, so this is terminal A1, this is terminal B1 and this is terminal C1, that is the winding voltages are A1 A2, B1 B2 and C1 C2. On the low voltage side, corresponding A1 A2 should be in phase with the voltage will be parallel to the voltage A1 A2, therefore in phase opposition. So, if we say this terminal is A1, the phasor A1 A2 will be in this direction. If this terminal is C1, then this is the voltage C1, and if this terminal is B1, then this is the voltage B1 B2. So, we see that the winding voltages B1 B2 and B1 B2 are in opposite phase. Therefore, if we see the winding connections like this A2, A1, B2, B1, C2, C1, the delta on the high voltage side is formed by connecting A1 to B2, then B1 to C2 and C1 to A2. And the lines are connected to A2, B2 and C2. These are the lines A, B, C. On the low voltage side also, this is A1, A2, B1, B2, C1, C2. However, the dots are now this way. That is, instead of A2 and capital A2 having the same instantaneous voltage, now A1 and A2 should have same instantaneous voltage, because we are seeing that the voltage V A2 A1 and the voltage V A2 A1 are should be in phase opposition. The connections are made again by connecting A1 to B2, B1 to C2 and C1 to A2, and the lines are connected to A2 B2 C2. So, this is the connection D D 6. Similarly, we can see how the connection DD0 or YY6 will look like. So, let us turn our attention to a slightly more complicated connection, let us say DZ0. So, again here we have the line to neutral voltage phasors. A, B, C. These are the line to neutral voltage phasors. If we assume the terminals are connected from A2, B2 and C2, then let us say this is A1. So, the winding voltage is A1 A2, B1 B2 and C1 C2. These are the winding voltages. Now, this is the delta side connection A2 B2 C2. Now, it is to be understood that in a zigzag transformer, each of the secondary winding has two parts. So, the voltage phasors A1 A2, there will be two voltage phasors, this is A1 A2 and A3 A4, which are parallel to the capital voltage capital A1 A2. Similarly, there will be two voltage phasors B1 B2 and B3 B4 and two voltage phasors C1 C2 and C3 C4. It is necessary to make the connection as DZ0, which means that the zigzag side line to neutral voltage should be in phase with the line to neutral voltage of the delta side. Therefore, the zigzag side line to neutral voltage should be, this is should be A, this should be B and this should be C. Now, in a zigzag transformer, each phase is formed by connecting two different winding sections. So, how the and these two different winding sections of belonging to two different phases. So, how can I construct this line to neutral voltage phasor of a zigzag winding using two different phase voltages? One of them will belong to the A phase, the other should be either B phase or C phase. So, it is usually the last one will be the A phase. So, let us say this is connected by connecting A4, A3. Then the other phase voltage must be this. Now, this phase voltage by comparing with this can be either C2 C1 or C3 C4. Generally, it is the first part that is taken. So, this will be C1 C2. Similarly, the B phase will be connected using B3 B4 as the last leg. this can be A2, A1, A2. C phase will be formed with C4, C3 as the last leg, and this will be B2, B1. So, if we look at the winding connection diagram, this is the high voltage side windings, this is A2, A1, B2, B1, C2, C1. The delta is formed by connecting A1 to B2, B1 to C2, and C1 to A2. These are the lines A, B, C. Now, on the low voltage side, you have two sets of winding here, one set, second set. This is A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4. Now, let us look at the phasor diagram. The star is formed by connecting A2, B2, C2. So, this is the neutral point on the zigzag side. The lines are taken from A4, B4, C4. So, this is terminal A, terminal B, and terminal C. Inside, we find that C1 is connected to A3, C1 should be connected to A3, similarly, A1 should be connected to B3, and B1 should be connected to C3. That completes the connection of a DZ 0 transformer. How do we get a DZ 6-degree transformer? DZ 6, again the line to neutral voltages are this on the delta side. So, this is the voltage phasor A1, A2, this is the voltage phasor C1, C2, and this is the voltage phasor B1, B2, this is terminal A, this is terminal C, this is terminal B. So, these are the voltage phasors. So, you will have two voltages A1, A2, A3, A4, then B1, B2, B3, B4. These are the different winding voltage phasors that we will obtain on the LV side. C1, C2, C3, C4. Now, the connection is DZ 6 degree. So, the line to neutral voltage phasor on the low voltage side will be, this will be A, this will be B, and this will be C. So, the last leg should be formed with a voltage phasor of A, and it should point towards this. So, this is formed by taking A3, A4. So, this is A3, A4. Then the next voltage phasor should be this. Obviously, this should be C2, C1. Similarly, the B voltage phasor should be formed with B3, B4, and this should be A1, A2, this should be formed with C3, C4, and this should be formed with B1, B2. Hence, the winding connection wise, This is A1, A2, B1, B2, C1, C2. The connection is A1 connected to B2, B1 connected to C2 and C1 connected to A2, and the supply is given to A2, B2, C2. On the zigzag side, you have two sets of windings, A1, A2, A3, A4. B1, B2, B3, B4, C1, C2, C3, C4. According to the phasor diagram, in this case the start point is formed by connecting A1, B1, C1. So, this is the start point and terminals are taken out from A3, B3, C3. So, these are the terminals taken out A, B and C. Connection wise, A2 is connected to B4, A2 is connected to B4, B2 is connected to C4, and C2 is connected to A4. So, this completes the connection of DZ 6. In similar manner, remaining connections can be easily drawn. Let us say what will be DD 0. DD 0 A, B, C, A2, B2, C2, this is C1 also, this is A1 and this is B1. So, this is the winding voltage phasor A1, A2, this is B1, B2 and this is C1, C2. DD 0 means line to neutral phasors are co-phasor, so will be the line to line phasors. So, on the secondary side, this will be the phasor, this will be another phasor and this will be another phasor. This will be A1, A2, this will be C1, C2, this will be B1, B2. Connection wise, the simple. This is A1, A2, B1, B2, C1, C2. Connections are made by connecting A1 to B2, B1 to C2 and C1 to A2. And the supply is given to A2, B2, C2. On the low voltage side, A1, A2, B1, B2, C1, C2. The connection is made by connecting A1 to B2, B1 to C2 and C1 to A2. This gives me the connection of DD0. Please compare this with the connection of DD6. Let us compare it with the connection of DD6. Here also the connection was similar, but here the polarity of the terminals, instantaneous polarity, were reversed. So, if this has to be reconnected into DD6, these connections are to be reversed. In other words, A2 has to be connected to B1, B2 has to be connected to C1 and C2 has to be connected to A1 and the supply is given to A1, B1, C1. That will give a connection of DD6. Similarly, we can obtain the connection of YY6, which is left as an exercise. Thank you.